All right, we're about to jump in and tackle a real beast of a coding problem. One of those ones that's labeled hard for a reason. It's designed to make you think. But that's exactly what we're going to do. We're going to take it apart, piece by piece, and turn what looks like a total mess into something clean, something elegant. Let's get into it.
Okay, so picture this. Imagine you've got a crystal ball, and it shows you a stock's prices for the next few days. The rules are simple. You're allowed to make exactly 2 trades. That's a buy and a sell, and then another buy and sell. The question is, how do you play your cards to walk away with the absolute most money possible? That's the heart of what we're trying to solve.
So let's make this real. Take a look at these prices. With 2 trades, the best you can possibly do is a profit of 7. But how? Well, you could buy when the price is low at 2, sell when it hits 6, boom, that's a $4 profit. Then, you see it bottom out at 0, so you buy again and sell at 3 for another $3. Add it up, you get 7. The real challenge, though, is how do we teach a computer to find that perfect path every single time?
To solve this properly, we first need to map out the maze we're navigating, because this isn't just about 2 transactions. The real problem is about handling any number of trades, a variable we're just going to call K.
So here it is, the official mission statement. We're given a list of stock prices and a number, K. Our job is to find the absolute maximum profit we can get by making, at most, K trades. So K buys and K sells.
Now there is one critical, non-negotiable rule that changes everything. You cannot own more than 1 share of the stock at a time. This means you have to think sequentially. You buy, then you must sell that stock before you're even allowed to think about buying again. Our entire strategy is built around this one constraint. Okay, so to make any smart decision in this maze, we need to know exactly where we are. We can define our state with just 3 little pieces of information. First, what day is it? Second, how many trades do we have left in our pocket? And third, maybe the most important one, are we currently holding a stock or do we have cash? These 3 things tell us everything we need to know. So where do we even begin? Well, the most intuitive place to start is to just consider every single possibility. Let's talk about this brute force idea, where we literally try to map out every choice we could make on every single day. If you think about it, on any given day, your choices are actually pretty simple. If you've got a stock in your hand, you have 2 options. Sell it at today's price or do nothing. Just wait. If your hands are empty, you can either buy a stock, if you've got trades left, of course, or again, just wait. When you start branching this out, you create this enormous tree of possibilities. And right here is where this simple, brute force idea completely hits a wall. Sure, it would eventually find the right answer, but it is painfully inefficient. Why? Because it keeps asking and answering the exact same questions over and over. It'll calculate the best profit from day 5 with 1 trade left, and then, later on, down a different path, it'll ask the exact same question and do all the work again. It's a massive waste of time.
This massive inefficiency leads us to our first huge breakthrough. If we're constantly solving the same little subproblem, why don't we just, remember the answer after the first time? This simple but incredibly powerful idea is called memoization.
Memoization sounds like a fancy, complicated term, but it's not. It's literally just creating a cheat sheet for your algorithm. The first time you figure out, say, the best profit from day 5 with 1 trade left while holding a stock, you just jot down the answer. The next time the code asks that same question, it doesn't have to do all the work again. It just looks up the answer on its cheat sheet. Simple as.
The difference here is night and day. Brute force is like having a terrible memory. It does the hard work again and again and again. Memoization is smart. It works out the answer once, and from then on, it's just a quick lookup. This one change takes our solution from being impossibly slow to something we can actually run. So, memorization is a huge improvement, but it's still what we'd call a top-down approach. We're kind of starting from the end and working our way back. But what if we flipped the whole problem on its head and started from the beginning, building our solution from the ground up? This brings us to a whole new way of thinking, dynamic programming. So instead of asking, what's the best I can do from today until the end, dynamic programming asks a different question. What's the best possible outcome I could have achieved up to this point? It starts on day 0, figures out the best profits, and then uses that information to figure out the best profits for day 1, and uses that to figure out day 2, building the solution forward, 1 day at a time.
Let's look at a quick example to see it in action. On day 0, the price is 3. If we buy, our profit is -3. If we don't, it's 0. Easy. Now on day 1, the price is 2. The best profit we could have had while holding is now -2, right? Because it's better to have bought at 2 than at 3. Then on day 2, the price is 6. Suddenly, the best profit while not holding jumps to 4, because we could have sold the stock we bought for 2. You see? Every new calculation only depends on the best answers from the day before.
This entire process is driven by two little formulas that are the engine of our solution. To get today's best profit without a stock, we just ask, what's better? Is it doing nothing and keeping yesterday's non-holding profit, or did we just sell today, which would be yesterday's holding profit plus today's selling price? We take the max. We do the same thing for our best profit while holding a stock. We are always just making the smartest choice based on the optimal decisions we made yesterday.
Okay, our solution is fast now, which is awesome. But it uses a lot of memory. We're building this big table storing results for every single day. So the question becomes, do we really need to keep all that history? This is where we get to the final, really elegant optimization. The key insight is so simple, but it's incredibly powerful. To calculate all the optimal profits for today, the only information we actually need are the optimal profits from yesterday. That's it. What happened the day before yesterday or a week ago, it's completely irrelevant for our next decision.
So the logic is pretty straightforward, right? If the only thing we need is yesterday's info, why on earth are we storing the results from every single day before that? We don't need to. We can just keep track of two sets of data, yesterday's results and the today's results we're working on. Once we finish today, it becomes the new yesterday, and we can just reuse the space. We never have to store the full history.
And the impact of this one little insight is just dramatic. Our memory usage absolutely plummets. It goes from being proportional to the number of days times the number of transactions, all the way down to being proportional to just the number of transactions. If you have years of price history, this is a total game changer.
So let's just zoom out for a second and look at the path we just took. We didn't just solve one tricky problem. What we really did was walk through a powerful, repeatable way of thinking that you can apply to tons of other complex challenges.
This is such a classic problem-solving blueprint. You start with the most intuitive, simplest idea you can think of, usually something recursive. If it's too slow, you make it faster by not repeating yourself, using memoization. Then, you step back and see if you can reframe the whole problem from the bottom up with dynamic programming. And finally, you give it that last polish by trimming away any data you don't actually need.
And after all that, after that whole journey, we come full circle, right back to our original example. Every single one of these methods, from the slowest brute force approach to our final lean optimized code, correctly lands on the answer 7. The difference was never about the destination. It was about finding an incredibly efficient path to get there. And that really is the biggest takeaway here. This journey from brute force to optimized DP is so much more than a solution to a stock problem. It's a mental toolkit. So the real question to leave you with is this. Now that you have this toolkit, what other complex problems out there can you start to crack using